Hello everyone, and thanks for joining Innovative Sensor Technology for our webinar on humidity measurement using thin film sensor technology. Here's a quick overview of what we'll cover. First, we'll review some humidity measurement terminology. Next, we'll take a look at some sensor types, then learn how they work. We'll then discuss some important factors in humidity measurement, like temperature compensation and calibration. Finally, we'll look at the fabrication flow for the P14 IST AG's all-rounder for humidity sensing. Let's get started with humidity. So, what is humidity? Humidity is a quantity representing the amount of water vapor in the atmosphere or in a gas. For this presentation, we'll be talking about humidity in air. Why do we measure it? We measure it because the amount of water present in the air can influence many physical, chemical, and biological processes. Some common application areas include HVAC, automotive, white goods, meteorology, medical equipment, and energy. Let's introduce some key humidity terminology first. Absolute humidity is the total amount of water vapor that's present in a unit volume of air. It's usually shown in grams per cubic meter. For reference, the maximum absolute humidity of warm air at 30 degrees C is approximately 30 grams per cubic meter. For cold air at 0 degrees C, this maximum absolute humidity is around 5 grams per cubic meter. In a fixed volume, the absolute humidity does not change with the air temperature. Relative humidity is used to describe how much humidity is present in the air compared to how much there could be. We usually see it expressed as a percentage RH, where 0% represents totally dry air and 100% means the air is very moist and that mist or dew is about to form. So, relative humidity is dependent on temperature, so it's necessary to measure temperature as well. The maximum amount of humidity in the air is also dependent on temperature. So at constant pressure, the maximum increases with temperature. While the amount of water in the air, the absolute humidity, might stay the same, a drop in temperature will lead to an increase in the relative humidity. Let's take an example. Imagine the lawn in the morning. The decrease in temperature overnight causes condensation to form, so you'll see dew on the grass when you wake up. This is because we reach the temperature where the relative humidity is 100%, so the water droplets start to form. This temperature is referred to as the dew point. In the same example, we see that RH is relatively high in the morning when the temperature is low, but it decreases throughout the day as the temperature increases. In the evening, the RH again starts increasing as the temperature decreases. What's a humidity sensor? A humidity sensor, sometimes referred to as a hydrometer, measures the amount of water in the air. To measure the relative humidity, we also need to know the temperature of the air. So we'll need to measure temperature as well, either with a separate sensor or with a humidity sensor with onboard temperature measurement. You can learn more about temperature measurement in our temperature sensor webinar. Pressure is also an influencer, so we'll want to measure this as well so we can calculate the relative humidity. For this presentation, we'll just be working with air at 1 atmosphere pressure. How does the sensor work? Thin film capacitive humidity sensors, like the ones from IST, consist of two metal plates which act as the electrodes. Between them, we have a polymer. This is a material made of long repeating chains of molecules. Its dielectric constant changes depending on how much moisture is absorbed inside. You might try to think of it as a sponge. It'll hold water in a moist environment until the water evaporates, then the sponge dries out. So, what are we measuring between our plates with this polymer? We're measuring capacitance. Capacitance is the property of a system which enables it to store an electrical charge. It depends on the distance between the electrodes, which in this case is the layer thickness of our polymer, the chemical nature of the material between our electrodes, this is the dielectric constant we introduced before, and the area of the electrodes. Capacitance is typically expressed in farads, named after the English physicist Michael Faraday. In our case, we'll be working with very small capacitance values in picofarads. We can calculate the capacitance using this formula, where capacitance is equal to the dielectric constant of our polymer times the area of the electrodes divided by the thickness of our polymer layer. Let's take a look at how we determine the humidity. A voltage is applied across the two electrodes. Water molecules from the air will pass through the holes on the porous top electrode. The polymer then collects the moisture, which causes a change in the electric field between the electrodes due to the change in dielectric constant of the polymer. An increase in water molecules inside the polymer means more charge can be stored in the system, so we'll read a higher capacitance. The opposite is also true. We can convert this capacitance to a relative humidity value using our characteristic curve and temperature value. So how are we usually capturing this? Here's an example circuit where we use a dual timer to obtain a linear pulse width modulated or PWM signal for our capacitance. In dark blue, we have our clock signal, setting the starting point for each measurement. In this case, we're using 10 kHz, which is our recommended maximum measurement frequency. The time per cycle is 0.1 milliseconds. Let's say we have an RH of 30% at 23 degrees C. Our PWM signal will then have a pulse of 0.03 milliseconds, which is 30% of the measurement cycle time. This represents 30% RH. So this is just one simple circuit example. Many of our customers choose to use other microcontroller-based solutions for their measurement. If you have any questions about integrating our humidity sensors in your setup, feel free to get in touch with us. Just like with our temperature sensors, each humidity sensor model has a characteristic curve. For most of our sensors, you'll see a pretty linear relationship between RH and capacitance. This is, however, temperature and pressure dependent. Assuming a constant pressure, we can calculate the temperature influence on our RH measurement using the formula at the bottom. The coefficients for each sensor model can be found on the corresponding data sheets. Now let's take a look at the sensors. At IST, they're broken into two main categories: passive elements and active modules. We'll talk about the passive elements first. These are capacitive humidity sensors without electronics. The customer will integrate these using their own electronics, and then they'll perform their own calibration. The readout signal in this case is capacitance. You'll notice in the pictures that the sensors come in different chip sizes with different wire materials and configurations. Surface mounted or SMD types are also available. There are several styles to choose from. While they all work the same way, they have different characteristics which make them suitable for certain application areas. Some of our standard sensors include the P14 family, the MK33, and the K5W. One of our newest sensors is the P14 4051 Rapid 2 Thermo. Let's take a closer look at the P14 series. These sensors have good chemical resistance, wide temperature range up to 150 degrees C, and fast recovery time. I'll point out a few sensor-specific highlights here. The general P14, available with SIL, round wires, or as an SMD, is our all-rounder, suitable for lots of applications. The P14 femtocap is available as an SMD and is good for white good applications due to its good price-performance ratio. Like the regular P14, the P14 Rapid is also available with SIL, wires, or as an SMD. It has ultra-fast response time and can be used down to -80 degrees C, making it a good choice for meteorological applications, like weather balloons. You may have noticed that the P14 Thermo sensors we saw in the beginning have 4 wires. That's because they have a temperature sensing element built in. The inner 2 wires are for this RTD element. Again, if you want to learn more about how the RTDs work, check out our previous webinar on RTD temperature sensors. We already know that the temperature influences our RH measurement, so it's great to have the RTD on board. The resistive element also works as a heater. This is useful in applications where you expect condensation. We can apply heat to evaporate this moisture, readying the sensor for its next measurement. These sensors have many of the same benefits as the P14, with the added benefit of the RTD/heater. First up, we have the P14 2FW Thermo. The onboard PT100 RTD makes it optimal for dew point applications and humidity generators, where we expect to have some condensation. Next, we have one of our new sensors, the P14 4051 Rapid 2 Thermo. It can be used down to -80 degrees C and has ultra-fast response and recovery times. For this sensor, the RTD element is located on the sensor backside. Next up, we have our MK33, which has a very wide operating temperature range and excellent chemical resistance. SIL and round wire versions are available for the MK33. It's optimal for high-end measuring applications and extreme environments, including measuring moisture content in oil. It can be used up to 190 degrees C. Finally, we have the K5W, which is super stable at low humidity. It has very small dimensions and high sensitivity. So you might ask, what's the real difference between these sensors? It mostly comes down to the polymer. We've developed several different polymers to be used for the capacitive layer. These were developed with particular applications in mind. The sensor construction also sets each one apart. As you can see below, we have several chip sizes and wire materials to choose from. Many customers prefer to use the wired sensors over the SMDs because they can provide some thermal insulation from the PCB material where they might be attached. Now, moving on to active humidity temperature modules. We call this product line our HYTs. These modules have integrated electronics and contain a capacitive humidity sensor plus a temperature sensor. IST performs the calibration in-house before shipment, so all you need to do is plug it into your controller and get going. The readout signal here is %RH and degrees C as a 14-bit digital I²C signal. As you can see below, there are several models to choose from, all suitable for different applications. On the right, we have our LCD module, which is useful for simple evaluation of the HYTs and easy integration with customer electronics. First, let's talk HYT basics. The sensors feature a P14 humidity sensor chip, like we discussed before. They have onboard temperature sensors and a good humidity and temperature range, measuring from 0 to 100% RH between -40 and plus 125 degrees C. They use the I²C protocol and are fully interchangeable. They come pre-calibrated using 9 humidity temperature reference points. They're also addressable, meaning we can connect up to 128 HYTs to one bus. Let's take a look at each version. First up, we have the HYT271, which is a good general purpose sensor. Example applications include handheld instruments, transmitters, and HVAC. Since the P14 element is exposed to the environment, it has the fastest response time. The body of the sensor, the blue part, is ceramic, which has better thermal transfer qualities than a resin or plastic-based module. The HYT221 is optimal for meteorology, industrial drying systems, agriculture, and medical devices, where we might expect to see some condensation. It features the same ceramic body material as the 271, but has a splash waterproof membrane filter to protect the sensor against condensation. Its round casing makes it easy to install in many applications. Finally, we have the HYT939. This is great for medical and drying systems, autoclaves, and pressure dew point measurement. Its casing makes it robust for high pressure or industrial applications. The sensor is protected by a metallic mesh filter. Just a quick note on working the HYTs into assemblies. HYT modules are often assembled into housings, probes, and cavities, depending on the module chosen and the application. The housing helps to protect the module from damage and increase robustness. Since they have a round encapsulation, the HYT221 and 939 are are generally mounted in cavities. I briefly mentioned the I2C communication protocol. Here's a little more on that. I2C was designed by Philips Semiconductors in the early 1980s and is used to connect integrated circuits. It stands for Inter-Integrated Circuit Communication. It's a common protocol which many devices use. It's a multi-master serial bus, which means we can connect multiple addressable sensors, and each one can initiate data transfer. As I mentioned before, HYTs are addressable, meaning we can connect up to 128 HYTs to a single bus. Also, I previously mentioned IST's HYT LCD module. With this, you can plug in an HYT 271 or 221 and get a quick readout of RH and temperature. It also delivers a 0 to 10 volt linearized output for easy integration. There are a few important guidelines and considerations to take note of when you're working with these capacitive humidity sensors and modules. You can get in touch with us to discuss your specific application in detail, but here are a few general points to be aware of. Calibration. For passive elements like the P14, you should hold off on calibration until 5 days after soldering at the earliest. You should also be sure that your humidity chamber is thermally uniform for an accurate calibration. Assembly. Be sure that your glues or casting materials are not too close to the sensing area. These can act as a humidity source and affect your measurements. Handling. When working with the passive elements or the HYT modules, be sure not to touch the active area of the sensor. This can introduce scratches or contamination, which can affect the sensor behavior. Our recommendation is to always use plastic tweezers, gripping the sensor by the wires, as shown here. If you don't have tweezers and you use your hands, be sure to wear gloves and avoid touching the sensing area. Here are a couple of other things to consider. Drift. Humidity sensors are exposed directly to their environment, with constant changing temperatures and countless airborne contaminants. The sensor can eventually start to exhibit drift. This can be minimized with a proper housing or by preconditioning the sensor. This typically involves exposing the sensor to VOC contaminants. Hysteresis. This is a condition where after some time there's a lag in the response and the sensor takes longer than usual to reach its expected state. If you'd like some application-specific recommendations, please get in touch with us and we'd be happy to discuss. You might ask, how do we make these tiny sensors? Just like with our other sensor types, we do this in a carefully controlled cleanroom environment. I'll give a quick overview for a P14 sensor. If you'd like a closer look at each process, I recommend checking out our temperature webinar, which goes a little more in depth. First, we start with our bare aluminum oxide substrate. Then we deposit our bottom electrode using a sputtering process. We remove some material using additional processes, including spin coating, photolithography, and etching. Unlike our temperature and flow sensors, the humidity sensors have several additional layers on the contacts. These are deposited and shaped using the same processes I previously mentioned. Next, we deposit the polymer with spin coating. The excess is removed using ion etching. Then we deposit the porous top electrode through a mask using a process called evaporation. When we remove the mask, we're nearly finished. Finally, we attach our wires. In this case, the SIL is positioned, then soldered. Again, this is just a quick overview. At IST, there's several additional steps involved, including cleaning processes, high temperature steps, and inspections. If you've seen our other webinars, you know that IST is known for building not just standard sensor components, but custom sensors as well. Here are a few ways we can customize a sensor for your particular application. First, we can change the wire style, material, and length. Here are a few common ones you'll see on our humidity sensors. The different wire types have different mechanical properties and are rated for different temperature ranges. If you have something special in mind, let us know. We can also customize the polymer itself. This changes the dielectric constant and influences the sensor behavior so we can fine-tune it in your application. Another way we can customize an HYT module is by using different calibration values based on your particular application. We have finely controlled humidity and temperature chambers in-house, so this is no problem. And that does it for humidity measurement using thin film sensor technology. Along with these sensors, IST also offers a variety of temperature, flow, conductivity, and biosensing components. We invite you to visit our website, www.ist-ag.com, and reach out to us to discuss your application. Our technical staff can discuss our many standard products and give you insight into our simple customization process. If you have any questions, please note our email address, info@ist-ag.com, where you can reach out to us anytime. Thank you everyone for watching. And again, feel free to contact us anytime to discuss your sensing needs. Check our website for your local contact info. You can also reach an IST team member using our website's live chat, available 24 hours a day, Monday through Friday.